we'll get started. Others join as we go along. So today we have this session on materials for energy transition. So myself, Ram Sethi, I'm faculty here at the Chemical Engineering Department. So I'll be chairing this session. And we have three speakers. One of them is joining online. She was not able to travel to Chennai. And we have other two who are here from the University of Sydney. So the first speaker is Tian. She is from the University of Exeter, and she will be speaking on solid-state hydrogen storage. Followed by we have Francois, a host in the University of Sydney. He'll talk about materials for hydrogen economy. And third, we have Antonio, who is also here from the University of Sydney, from the Faculty of Engineering. So he will talk about global green hydrogen. So all that is connected with hydrogen, all the three speakers. So we'll first start with Tian. Tian, are you online?
Yes, here.
Okay. Nice meeting you. So Tian is a senior lecturer in the University of Exeter, and she's heading the research on the hydrogen storage at the University of Exeter. So her research is concerned with understanding the structure-property relationship of functional composites and their application to potential problems in sustainable energies. And she has significantly contributed to the development of porous polymer composites for onboard hydrogen storage system, which has a direct impact on lightweight vehicles and low carbon economy. And she has been leading the research on the neutron scattering technique for hydrogen energy material, which provides the fundamental properties of hydrogen, and also hence which can lead to the novel hydrogen materials by design. And she has received several prizes, and she is also named as one of the top 50 women in engineering in 2020. And she is also an NTSRC ambassador for women in engineering in 2023. With these few words, I request Tian to share a presentation and talk.
Can you see my screen?
Yes. You can go ahead.
Can you hear me?
Yes.
Oh, good, lovely. So good morning, everyone. My name is Tian. Thank you for Professor Chatty for the introduction. It's a great honor to connect with you virtually today at this prestigious IIT Energy Summit in Chennai. Well, I'm deeply regret not being able to join you in person, but I'm grateful for the opportunity to share my research on solid-state hydrogen storage through this online platform. So before we dive into the hydrogen storage, I'd like to kick off with the bridging the distance between us. So I'm based in Exeter in the UK, which is located approximately 5,000 miles away from China, and has a 5 hours and 30 minutes time difference. So I'm now at the moment is early morning in the UK. So our University of Exeter, is a hub for pioneering research, especially in fields like the one we are exploring today. So my research focus on hydrogen energy with 4 research themes. The first one is synthesis, sustainable chemistry and green synthesis, the composite for hydrogen storage and transportation. Also have a special research expertise in neutron advanced characterization, namely neutron scattering, using in-situ neutron scattering to investigate hydrogen interaction with solid states, with solid surface to at a molecular and even atomic level to really break through fundamentally the mechanism of hydrogen storage. So let's take take a look at the broader picture of hydrogen in the UK's energy landscape. So UK has been actively shaping a sustainable future through various hydrogen-focused policies. In 2019, the government announced a net zero commitment by 2050, and followed by the Prime Minister's 10-point plan in 2020, which aimed for 5 gigawatt of low-carbon hydrogen production to fuel a green industry revolution. In 2021, the UK had launched its first hydrogen strategy. And just a year later, it ambitiously doubled the target from 5 gigawatt to 10 gigawatt low carbon hydrogen production. So hydrogen has been recognized as contribute to national energy security. So my view is, in the future energy system, hydrogen will play a significant role both nationally and globally, serving as a clean fuel and for large-scale renewable energy storage and a pillar of energy security. So hydrogen is not really far from us. We can find a lot of hydrogen products on the market already. For example, hydrogen battery chargers, hydrogen refilling station, hydrogen fuel cell EV cars, and even hydrogen boilers in the UK. So how does this work? Is actually very easy. Hydrogen can be produced from water splitting using water electrolysis through the renewable generated electricity. So the idea is you bring your water, you split the water into hydrogen and oxygen, and then you can use hydrogen to power your car, your house, whatever need energy to drive. And then hydrogen will be converted into water again. So you can see this is a completely green cycle. Water comes in and out, and there's no carbon emission. So hydrogen has a great potential to be amazing. However, how to store and deliver hydrogen still keep significant technical challenges. So if we look at this energy density table, and we can see more clearly where the problem is. So if you consider gravimetric density, the x-axis, which is the amount of energy per unit weight, hydrogen is outstanding, offering 3 times the energy density of petrol. Okay, and this is where hydrogen potential really shines. However, the story changes when we look at volumetric density, and the volumetric density is the amount of energy per unit volume. Here, hydrogen is neglectable. With the volume density so low, that becomes a really critical issue. To match the energy capacity of petrol, we need a much larger volume hydrogen, which poses a significant challenge for storage and transportation. So if you look at these 2 photos, the hand side photo is the hydrogen bus running in London, and we can see 4 huge high pressure hydrogen tanks sitting on top of bus, which working with the working temp pressure at 700 atmospheric pressure. And comparing with the size of the private car next to it, you can see directly where the problem is. And the second classical way to store hydrogen is liquefy hydrogen. But liquefying hydrogen requires extremely low temperature at minus 253 degrees Celsius. So you can see both methods poses a serious risk issues and also offer a huge energy penalty. So we want to solve the problem by store hydrogen in solid state. And to achieve solid state hydrogen is actually very difficult. You need to really pressurize to extremely high pressure for 400 gigapascal or really low temperature, 14 Kelvin. This is generally impossible practically in industry. So we found we can use nanoporous materials. Using confinement of nanoporous materials, stabilize and freeze hydrogen molecules at a relatively milder condition. So we develop a novel, innovative material we call molecular sponge. So a sponge can absorb water. So our molecular sponge is designed to absorb hydrogen. So the key characters is, I'm just trying to play this video. The key characters of the this molecular sponge nanoporous materials is incredible small pores and vast surface area, which are engineered to maximize the hydrogen absorption. When hydrogen is introduced to this nanoporous materials, the molecules are spontaneously absorbed and compressed into this nanospace. And this process results in extremely high hydrogen density, and we wouldn't be able to achieve through conventional means. Importantly, this absorption is reversible process, which can be controlled by adjusting temperature or pressure. So this flexibility is crucial for practical hydrogen storage and release. However, one of the key challenges to develop this technology, this material, is how to characterize hydrogen, because hydrogen is invisible gas and is insensitive to the lab-based technique, for example, X-ray diffraction. Therefore, we employed neutron scattering, using neutron to see through hydrogen, because neutron is highly sensitive to hydrogen molecules, and the neutron has can penetrate everything. So, for example, neutron can penetrate the sample environment of the cross stat and sample holder, and the sample itself directly probe hydrogen inside the material, making it a really powerful tool and ideal tool for develop hydrogen storage materials. And through the neutron scattering, we discovered we can in some special materials, this hydrogen can be solidified. Hydrogen can achieve solid-like state in a relatively milder condition. For example, at 77 Kelvin, that is liquid nitrogen temperature, and at a relatively much lower pressure. So our insight into hydrogen storage has been greatly enhanced by neutron analysis, coupled with molecular simulation. So molecular simulation really allows us to visualize and understand how hydrogen behaves within the pores of our material. For example, in this image displayed, the golden balls represent hydrogen molecules. The gray sticks represent the porous framework. It evidences that hydrogen can form a highly ordered two-layer structure within slit-shaped pores at 0.66 nanometer. And these slit pores dimensions are ideal for tightly packing hydrogen, immobilizing the molecules, and create a solid state hydrogen. Conversely, under the same condition, hydrogen behaves differently in cylindrical pores, showing in the right side figure. There, the hydrogen form spiral structures with higher mobility and lower density. And these observations are critical for us to identify the optimal pore structure when designing materials for hydrogen storage. So based on our theoretical study, and we then are able to conceptualize the next generation of high capacity hydrogen storage tank for onboard system. Presently, type 4 hydrogen tank are used in onboard system. These are carbon fiber reinforced polymer as a liner, as outer layer, lined with high density polymer layer working at 700 bar. So our technique involves integrating the molecular sponge, the material developed as a liner into this type 4 tanks. So the goal is to enhance hydrogen storage capacity significantly while simultaneously reducing risks, ensuring a safer and more cost-effective solution for hydrogen-powered system. And this leads us to the actual materials that will really revolutionize our approach to deliver this new generation hydrogen tank. So here we present the top 4 composite membranes our team has developed. And these membranes are not only self-supporting and durable, but also precisely engineered with the optimal pore size and porous structure required for efficient hydrogen storage. And we did a lot of the measurements, which including the mechanical property testing, like demonstrated impressive integrity, holding strong under various stresses. And however, it's important to note their mechanical properties tends to decrease as we increase the concentration of porous fillers. Despite this, they maintain stability up to 200 degrees Celsius in air, showing their resilience. Of course, we care about how much our material can, how much hydrogen our material can store, and then we carried out high pressure hydrogen measurement, and our leading composite membrane showcases a storage capacity of over 6%. And this achievement surpasses the Department of Energy's target of 4.5%. However, translating this capacity into practical usable techniques requires more than just the membranes. So this brings us to our next major development. We are now nearing a path from membranes to composite modulus to shaping it. And so, for example, you can see we are working from the powder and the yellow powder to membrane, and now we are trying to structure in a large scale. And this evolution is critical for adapting our material to fit within high-pressure tanks, a necessary step for real-world application. And you can see from this photo from powder to membrane and to modulus, and we also did a lot of testing on the properties, stabilities, mechanical property, etc. So I hope I'm still on time. So to summarize, within the constraints of this very brief presentation, I hope to convey the following key points. First, we've successfully engineered a cutting-edge hydrogen tank with significantly improved energy capacity and safety features. Secondly, our robust research capacities in the field of hydrogen energy have not only resulted in the theoretical advances, but also translated into practical engineering solutions. Our aim is to lead technology innovation and turn state-of-the-art technology into a whole renewable energy system regionally and nationally. And our long-term vision is to collaborate with our communities, government, industry partners and international partners like IIT to test and deliver interdisciplinary solutions in the field of renewable energy and hydrogen nationally and internationally. And I'd like to also take this opportunity to acknowledge all my collaborators for their contribution to these projects and all the financial support from research councils. And finally, I would like to announce we are now recruiting PDRA in hydrogen storage, and the closing date is very soon. And also we offer a full PhD scholarship. So if you are interested, feel free to get contact with me or get to the link, get to the website to find more details. And I think, yeah, that's the end of my talk. Thank you very much for your attention. I'm here for questions session. Thank you.
Yeah, thank you, Tian, I think, for the nice talk. I think also surpassing the DOE target of with your material reaching to 6.368%. We will take one or two quick questions. Yeah, Francois.
Thank you, Dr. Tian, for your talk. Can you, the storage capacity, at which temperature is that?
Sorry, say it again. Capacity.
The storage capacity of 6.8%, at which temperature is that? 77 Kelvin?
At what temperature is this storage capacity?
That is at 77 Kelvin.
So another question, why do you focus so much on the mechanical properties? You should be focusing on the heat management, because 77 Kelvin is pretty cold.
Well, it's not ideal at room temperature. Yeah, so we are trying to develop the room temperature ones, but it's still in development and not yet to the commercialization level. And actually the idea is at 77K is to combine with the hydrogen refilling process, because the current refilling is using a really high hydrogen flow rate, which generate the temperature increasing while during hydrogen adsorption process inside the tank. Therefore, before the refilling into the onboard system, hydrogen will have the cooling down process. So now I think that the main stream in hydrogen storage for onboard system is to cryogenic refilling, which means during the refilling stage, the temperature will be around 77 Kelvin. I know it's still not ideal, and our aim is really to deliver room temperature hydrogen storage solutions. But at the moment, it's really difficult. The temperature hydrogen is just really active and very sensitive to temperature. And the temperature increase gonna to reduce its capacity significantly. But that's really a good question, sharp question. Thank you.
Thank you. Any other questions? Yeah,
this is actually very interesting topic, this solid state hydrogens, and with respect to this purity of hydrogens, whether this we are storing at this composite membranes and molecular sieves, with respect to different temperature and pressure, this will have any impact on the quality purity?
Yes, it's influence. It's how we're gonna to shape it. Actually, it's not very easy for shaping it into column, into different shapes. That's actually limits its a design, limits its application. And it's the porous polymer we are using actually is not feasible for 3D printing. So we are now trying different polymers like PA12, which can be printed out and then to manufacture as a different shape and using composite. But so I'm not an expert in manufacturing, and really bring the material engineering level to manufacturing is completely different problem, different activity. There's a lot of the problems and challenges in shaping it, and which will greatly influence the properties of hydrogen storage and the mechanical properties. Not all the polymers can be used. Most of polymers actually will block the pores, so it's not usable. So we tested a lot of different polymers, and then identified this porous polymer. And after making the membrane, we realized it's so difficult to make the to make it into different shape. So it's the talk is really quite quick and brave. There's a lot of details. Actually, I couldn't really touch. So it's a really complicated question. Not only hydrogen storage. Every features we change, every composite concentration we change will influence its property, from the mechanical property, from the stability, and from and to its hydrogen behavior. And some material also suffer from very slow kinetics. It takes ages to absorb and discharge, which is quite useless. Even they have a high hydrogen storage capacity, but it's just too slow. We cannot really use it. So it's a complicated question, and there's a lot of parameters into research we need to consider.
Thank you, Tian. I think because of the shortage of time, I think we'll stop the questions here. We will move on to the next speaker. Thanks for joining us.
Yeah, thank you.